In Section 8 of Chapter 18, we will be discussing electrolysis. So far in Chapter 18, we have discussed galvanic cells, where chemical energy is changed to electrical energy. The galvanic cell uses a spontaneous redox reaction to produce a current that can be used to do work. The cell potential is positive. Now in Section 8, we are going to look at an electrolytic cell. This uses electrical energy to produce a chemical change. It involves a process called electrolysis, where an electric current is forced through a cell to produce a chemical change for which the cell potential is negative. The electrical work causes an otherwise non-spontaneous chemical reaction to occur. Here's a quick breakdown of the difference between a galvanic and an electrolytic cell. Here are two diagrams illustrating the difference between a galvanic cell and an electrolytic cell. In diagram A, this is our galvanic cell. It runs spontaneously to produce 1.10 volts. Our anode is zinc and our cathode is copper. The zinc is oxidized and the copper is reduced. When the zinc is oxidized, a whole bunch of zinc ions are around this zinc anode. Remember, zinc metal forms zinc ion when zinc is oxidized. So around this zinc anode, there's a whole bunch of the zinc ion. And that's positively charged. So then anions from the other compartment travel over because they are negatively charged and attracted to the positively charged zinc ions. When the copper ion is reduced, it gains electrons and forms copper metal. And so a whole bunch of copper ions will plate right here on our copper cathode. So that doesn't leave a lot of these copper ions surrounding the copper cathode, and there's just a lot of negative ions, a lot of sulfate ions there. And so then cations from the other compartment that are positively charged will attract to the negative sulfate ions in the cathode compartment. In diagram B, we have an electrolytic cell. Electrical energy is used to produce a chemical change. You can see there's a power source here, and this power source has to be greater than 1.10 volts. We're using the same substances in both cells. In the electrolytic cell, we are forcing electrons to go from the copper to the zinc this time. This is the opposite of the galvanic cell. So in the electrolytic cell, we are forcing a non-spontaneous chemical reaction to occur. Notice how the anode and the cathode have been reversed between the two cells because electrons need to flow from anode to cathode. Notice that the ion flow has also been reversed as well. So as electrons come over to the cathode, we will be losing zinc ions this time, and zinc metal will plate on our cathode. And so the cations will be attracted to the sulfate ions that are over here in this compartment. And then on the anode side, we will be producing more of these copper 2+ ions, and so then the anions from the other compartment will be attracted to those positive ions. Let's say we wanted to determine the mass of copper that would be plated when a certain current is applied over a given period of time. For this, we will look at the stoichiometry of electrolysis. First, we'll look at the current and the time. For current, we use the amp. An amp is a coulomb of charge per second. So if we look at our amps and we multiply that by our time in seconds, then we have our coulombs of charge. Once we have the coulombs of charge, we can use the Faraday to convert to moles of electrons. Remember, we used the Faraday when we calculated the free energy for a redox reaction. A Faraday is 96,485 coulombs per mole of electrons. So we can take our coulombs and cancel them, leaving us with our moles of electrons. Once we know our moles of electrons, then we can find our moles of copper. So we take our moles of electrons, and then we'll cancel them. Looking at our chemical equation, this particular one has 2 electrons. So this could vary from problem to problem, of course, but 2 moles of electrons will give you 1 mole of your metal. In this case, it's copper. And of course, once you know your moles of copper, you can convert to grams of copper using the molar mass from the periodic table. So to summarize, we would need to be given a current in amps and an amount of time that runs. We can change that into coulombs of charge, which we can use the Faraday constant to find the moles of the electrons with. And from the moles of electrons in our equation, we can find our moles of our metal. And then from moles, we can go to grams using the molar mass from the periodic table. So let's apply this process to this problem. How long must a current of 5 amps be applied to a solution of silver ions to produce 10.5 grams of silver atoms? This is kind of the reverse of what we just talked about. We know the mass of metal that we would like to produce. We want to go back and look at how long we need to apply our current of 5 amps. So if I know my grams of silver, I can find my moles of silver. 107.87 is the molar mass for silver. For every 1 mole of silver made, I need 1 mole of electrons to do that. I know it's 1 mole because my silver ions have a +1 charge. And looking at my Faraday constant, 1 mole of electrons, 96,485 coulombs. That will give me my answer in coulombs. I get 9,392 coulombs. I take my coulombs and I plug it into my equation with amps. Amps are coulombs per second. So 5 amps equals 9,392 coulombs over x seconds. If I solve for x seconds, I get 1,878 seconds. And I put that in minutes just to make it a little bit more manageable. 31.3 minutes. Now let's use the stoichiometry of electrolytic processes to find the identity of an unknown metal. We know that it took 52.8 seconds of current, that's at 2 amps, to plate 0.0719 grams of the metal from a solution that contains that metal nitrate. And we can see that that metal is going to have a +3 charge. So we'd like to identify the metal. Usually, when we're thinking about trying to identify something, molar mass is really useful. So if we knew our grams of our metal, which we do, and we could solve for the moles of that metal, we could take the grams and divide by the moles and get the molar mass. So that's going to kind of be our path here. We'd like to find the moles of our metal. An amp is a coulomb per second, so 2 amps equals my coulombs, I'm going to call that C for my variable, over 52.8 seconds. And I get 105.6 coulombs. I'm not going to round that just yet. I'm going to wait till the end to round. 105.6 coulombs I convert to moles of electrons using the Faraday, 96,485 coulombs per mole of electrons. And then I cancel my moles of electrons and go to moles of metal. Now, we know that the metal has a +3 charge because of the 3 that we see right here in the chemical formula. So I know that 3 moles of electrons must have been transferred to make the metal ion into the metal atom. That gives me 3.65 times 10 to the negative fourth moles of metal. So now I know my grams of metal and my moles of metal. If I divide them out, that will give me my molar mass. I get 197 grams per mole, and if you look at the periodic table, that is very close to the molar mass of gold. Now let's talk about electrolysis if we have a mixture of ions. Let's say that we have 0.10 molar of each of the following ions. We're going to predict the order in which the metals will plate out as our voltage is turned up from 0, so as we're applying an electric current. Do these metals form on the cathode or the anode? And explain. Well, let's take a look at the cell potentials given in the standard reduction potentials table. That's table 18.1. Here are the voltages for turning these metal ions into metal atoms. Remember from earlier in the chapter when we were looking at half reactions, the more positive the cell potential or the more positive the voltage, the more likely it was to be your reduction reaction. So copper is the only positive one here. That one is going to plate out first. The reduction of copper is the easiest. Now we start looking at the negative ones, and we are just going to go in order. This will be our second, this will be our third, fourth, and last. Once the voltage is greater than 0.13 volts, the lead will plate out 0.14 volts for the tin, 0.23 volts for the nickel, and once the voltage is greater than 0.76 volts, the zinc will plate out. The metals form on the cathode, as usual, when we're talking about reduction. You could also answer this question in terms of oxidizing ability, or the ability to be an oxidizing agent, and the order would be the same. Remember, an oxidizing agent accepts electrons.